All right, good afternoon. How is everybody doing today?
Good.
Great. Well, my name is Reggie Bain. I'm a senior at the USC Honors College. I'm studying physics and mathematics. And with my friend Jim Talbert, who's in the audience today, I co-founded Carolina Science Outreach just about 2 years ago. And we are an organization dedicated to sharing and popularizing scientific ideas throughout South Carolina. And thank you, Kevin, for having us today. And it's funny that they just presented this, showed this Math Magician TED video, because just about a month ago we had Dr. Benjamin perform this very show at USC in Gambrell Hall. I know Kevin was in attendance. I'm not sure if some of the rest of you were as well, but it was a fantastic event. But anyway, today I would like to talk a little bit about one of my favorite topics in physics, and that is the wonderfully amazing nature of our universe. And if we can get the slides going here, I call it To Infinity and Beyond because, at least from our perspective, the universe seems so infinitely large. And this is actually a picture taken by the Hubble Space Telescope of a beautiful nebula called the Crab Nebula. So, this is, in my opinion, an extremely inspiring photo. It's another image taken by the Hubble Space Telescope, which orbits around the Earth. And it is a deep field image of the universe from a faraway perspective, in a sense. Each point of light is not merely an individual star, but an entire galaxy, a collection of millions of stars, asteroids, comets, planets, pulsars, quasars, and all sorts of other really cool things. So, the three things I would really like to communicate with you all today are, one, kind of how our universe has evolved from its inception to where it is today. And also I'd like to share with you the vision of perhaps my favorite physicist, one of the really greatest minds in the history of science, that being Albert Einstein. And then I would like to talk a little bit about stars. They are one of the most important structures in our universe and are essential to our life, all life. So we begin with what science tells us created the universe, the so-called Big Bang. Supposedly, at the beginning of time, the universe was not as it is today, this vast entity, but a small, infinitesimally small, yet infinitely heavy, tiny little nugget that at some point exploded in a mass of energy, creating all of the mass and energy that we have in our universe today. And now, where do we fit in? Where is the Earth? How can we find us in this vast cosmos? Now, we must first look to one of the bigger structures that astronomers have kind of classified the universe through, and they're called galaxy clusters. Now, our galaxy cluster is called the local group, and within the local group you can find several large galaxies, such as our neighbor, the Andromeda Galaxy, as well as our own Milky Way. Now, on the very outside of one of its beautiful spiral arms of the Milky Way, you can find our solar system. 9 or 8, depending on your point of view, planets circling around the sun in perfect elliptical orbits. Now, one of the most important things for Earth's ability to sustain life and all these sorts of things is the sun. The sun and stars throughout the universe provide energy, light, and heat. Now, what process powers the sun? What allows it to provide us with sunlight and thermal energy to sustain life? Now, the process is nuclear fusion. I'm sure many of you have at least heard of it. It's used in hydrogen bombs, which aren't being created anymore, luckily. But the process of fusion is relatively simple. If you take the fact that all matter in the universe is made up of these tiny little bits called atoms, and that atoms are structures made up of a swirling cloud of what are called electrons, tiny particles, swirling around a tightly compacted nucleus of even smaller particles called protons and neutrons. Now, the process of fusion uses hydrogen, the simplest element of the universe, and specifically two different, or what are called isotopes of hydrogen. Isotopes are simply atoms with the same number of protons, but different number of neutrons and thus different weights present in their nucleus. In this case, we have deuterium and tritium, two isotopes of hydrogen that in a star get really close together, start to heat up, and ultimately fuse into a helium atom, and in the process releasing a vast amount of energy. Now, what drives this process? What causes these atoms, these particles within the sun, within a star, to get so close together that they actually fuse into one? The answer may surprise you. The answer is gravity. Isaac Newton first proposed the idea of gravity, his law of universal gravitation, in the 1680s in his Principia. And while he is really the father of physics in many ways, and in fact, in the same work where he introduced the laws of gravity, he also laid down the foundations of a very important branch of mathematics called calculus. Newton was actually harboring an embarrassing secret. He had no idea how gravity actually worked. It was this kind of, as scientists have put it since then, a, quote, spooky action at a distance. Gravity kept the Earth in orbit around the sun, the moon in orbit around the Earth, and the tides coming in and out. But how did it actually work? How did the sun know the Earth was there? How did the Earth know the moon was there? And it wasn't until hundreds of years later, in the 1920s, one other very famous physicist, Albert Einstein, with his very flattering picture here, really recast the laws of gravity and helped us to really understand how they work. Through his special and general theories of relativity, he revolutionized physics in so many different ways. Now, in 1905, in his what is now referred to as his miracle year, Einstein introduced his laws of special relativity. And they give rise to some very interesting and puzzling consequences. One of which is at least generally called the twin paradox, although it is not actually a paradox because it is fairly easily resolvable. Now, the twin paradox poses two identical twins, both starting on Earth at they're the same age, obviously. So, according to Einstein's special relativity, the speed of light is a sort of cosmic speed limit. Nothing in the universe can ever travel faster than the speed of light. And when you put this restriction on physics, some very bizarre things happen to the nature of space and time. In fact, it has been experimentally proven over and over again that if one travels closer and closer to the speed of light, the passage of time actually slows down. So the twin paradox consists of two twins, one remaining on Earth and one traveling in a spaceship, perhaps the Starship Enterprise or something, close to the speed of light to the closest star, Proxima Centauri, to us, and back again. Now, whereas he was the same age as his brother to begin with, when he returns to Earth after his long journey, he will be maybe just a few years older, depending on how long he's been for. However, his brother, who remained on Earth, who was not moving close to the speed of light, will have aged decades or even centuries, whereas the brother who was traveling is barely any older. This is just one of the fascinating concepts that Einstein introduced with special relativity. Now, what I really wanted to focus on is how he recast the laws of gravity. Gravity is this very familiar force that is inherent in nature that supposedly caused an apple to supposedly fall on Newton's head, which supposedly inspired him. It keeps the Earth in orbit around the sun and all these things we've already discussed. But Einstein was the first to really understand it. He proposed that we think of space and time as an intricately interwoven fabric. One affects the other and vice versa. And he said that gravity was actually the sort of bending and warping of this space-time fabric. Essentially what you want to do is imagine space and time as the surface of a trampoline. Imagine taking a bowling ball and putting it in the center of a trampoline. And the trampoline bends and warps to accommodate the bowling ball's mass. The same thing would happen if you, say, put a lighter object, like a baseball, in the center. However, space and time would warp less. So the more massive an object, the more it bends space and time. And thus, the more gravitational force it can exert. This was an absolute revolution in how we think about the universe, and has made so countless perfectly accurate predictions about many different experiments. It's given us a ton of insight. This is one of the cool kind of borderline science fiction topics that come out of Einstein's theories of general relativity, and it's called a wormhole. If any of you have ever seen Contact or really any Star Trek series, these come up all the time. The idea of a wormhole, while the existence of one has not been found, is that space and time in two different places in space warp so severely that they actually rip and connect, creating a sort of bridge from two seemingly distant places in the cosmos. Now, to talk a little bit more about one of the most important phenomena in the universe, and that is stars. And Einstein's theories of general relativity are fundamental to how stars form and how stars die, and without which we wouldn't be able to really understand a lot of modern astrophysics. Stars are born in what are called stellar nurseries, giant clouds of gas and dust sitting out there in the universe. And all of these particles, all these gas and dust particles, attract each other, and they get so hot and so close together that ultimately they start producing fusion reactions, start to light up, and ultimately form stars. Now, one of the most interesting parts of stars is how they die. And one way in which very massive stars die is a process called supernova. It is the largest explosions, with the exception of the Big Bang, that our universe ever sees. And when these supermassive stars die out and run out of fuel, they release all of their energy in this massive explosion that we can see from light years and light years away. But the most fascinating thing about supernovas, in my opinion, is that if you consider, say, a human or any organic life, where all of our atoms and molecules, we are primarily composed of carbon, nitrogen, oxygen, these atoms with multiple protons and neutrons in their nuclei. Now, the only place in nature that we have found where there is enough energy to produce such atoms is in these types of explosions, these supernovae. So the famous science popularizer Carl Sagan once said that we are all stardust. The atoms that make up each and every one of us were once formed in the depths of stars. This is actually, in fact, the Crab Nebula. The picture I showed you earlier on the first slide is actually the remnant of a supernova. So other interesting phenomena in the universe are binary star systems. If you've ever seen the movie Star Wars, the original one, you can see Luke Skywalker looking off into the distance, and he on Tatooine, and he sees two suns setting rather than just one. Now, while this seems like total science fiction, it actually does happen. We've seen it in the universe. Binary star systems often occur when an almost dead star, this is what our sun will become, it'll become what's called a white dwarf. A very heavy, very dense, but rather small remnant of a star. And in this binary system, a red giant star, the energy is actually being sucked off onto this white dwarf. White dwarfs are so dense, in fact, that a 150-pound person on Earth would weigh something on the order of 50 million pounds on a white dwarf star because its gravity, its gravitational force is so great. And another one of the coolest phenomena in the universe is the idea of a black hole. So imagine if you were to, when we talked about putting a bowling ball on a trampoline, take that bowling ball and replace it with something of the same size, but that weighed 50,000 pounds. It would warp your trampoline so greatly that it would likely rip. But imagine that it didn't. Imagine that you were able to pull the trampoline down to where it was isolated to this tiny single point. So take an infinitely heavy and infinitely small object. And this happens in the universe. Some of these supermassive stars that don't go supernova and explode will collapse upon themselves and warp space and time so great and so terribly that nothing, the gravitational force is so strong that nothing, not even light, can escape the gravitational pull of a black hole. And it actually is believed that the center of the Milky Way galaxy, located at the center, is a black hole that they call Sagittarius A. So the universe is filled with so many amazingly beautiful and intricate entities and bodies, and the universe is so immense and so awe-inspiring to me that looking at these sorts of pictures, studying the ideas of great minds like Einstein and Newton inspires me on a daily basis. And I would like to, again, thank Kevin for inviting Carolina Science Outreach today, and for all of you for attending. Thank you very much.